we can look at another notation that gives us a little bit more of an idea of what's actually happening with the electrons. And that's orbital notation. So let's stick with our oxygen example of how to use orbital notation, and we're going to bring in some more of the rules here. First of all, we know that oxygen has a 1s sublevel, it has a 2s sublevel, and a 2p sublevel. Now we also know that each s sublevel has 1 orbital, and each p sublevel has 3 orbitals. Now I'm going to go ahead and fill in the electrons where they belong. Again, I know I have 8 electrons. The first rule that comes into play is always Aufbau. That means I have to fill up the lowest energy one first, so that's my 1s. So I'm going to put 1 electron, and I represent it with this half arrow. I'm going to put my second electron in here as well because I know an orbital can hold 2 electrons. But the second rule that comes into play is called the Pauli exclusion principle. The Pauli exclusion principle says that each orbital can have at maximum 2 electrons, but that they have opposite spins. So I'm going to continue here. Aufbau says I go to 2s next. When I get to 2p, I'm going to do the same thing, but I have 4 electrons. So the question is, do I put 2, 2, and then 0 in the last space, or do I spread them out? And the third rule is called Hund's rule. It's helpful to think of Hund's rule as the subway rule or the bus rule, because just like strangers getting onto a bus or a train, they typically sit far apart from each other, they spread out before they sit next to each other. So electrons are going to behave the same way. We're going to put 1 electron in each orbital before we double up. That's Hund's rule. And notice I put them all with the same spin. Now I have 1 electron left over, and now I'm going to go back and double up. And according to Pauli exclusion, it's going to be the opposite spin of what's already in that orbital. So this is the orbital notation for oxygen. Now so far oxygen doesn't have that many sublevels, so it hasn't been that difficult to write out. But for some elements they have a lot of sublevels. So we have something called noble gas configuration as a way of sort of shorthand writing out the electron configuration, or the orbital notation. So let's look at scandium, which is element 21. It's right here. So we have 21 electrons for scandium. If we were to go through and write out our notation for this, we would end up with something really long. So 1s2 would fill up, 2s2 would fill up, we would have 2p6, 3s2, 3p6, and 4s2, and then we would get a 3d1. Okay, that would bring us here, 3d1. So if I write this out, we're going to get something that looks like this. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. That's pretty long. So you can see we're going to need a shorter way of writing this out, otherwise we're going to use up quite a lot of paper just writing out electron configurations. So how can we make this sort of a shorthand? Well, we take advantage of the noble gases. Those are the group 8 elements. Group 8 is this column right here, all the way on the right side. This is group 8. Okay, these are the noble gases. And what we do is we use them as sort of a starting point for our notation. So here's our example, scandium. The noble gas that comes right before scandium is argon, Ar, number 18. So here's what we can do. Instead of writing out this big long sequence, we instead write Ar in brackets, saying that we have the configuration of argon, plus a 4s2 and a 3d1. Okay? This part comes after the noble gas. And this becomes our noble gas configuration, and this is a much more convenient way of representing how the electrons are arranged in the atom. The last thing we're going to look at is 2 exceptions to the Aufbau principle. Chromium and copper are 2 notable exceptions that is useful for us to look at and see why they're exceptions and what about it makes them different. Here's what we would think the configurations are. We have chromium, and again I'm using noble gas configuration here. So chromium has argon's configuration plus a 3s2, a 2p6, 4s2, and 3d4. That's what we would think is the case. However, what really happens is that one of these electrons from the 4s2 gets promoted to the 3d sublevel. And that gives us this. So let's cross that out. And that gives us 4s1, 3d5. Now why is that? Well, we can take a look at, let's take a look at 4s, and we'll have the 5 orbitals that are 3d. Okay, this is our orbital notation. We'll take a look at what's going on here. So what we ended up with was 1 electron in 4s and 5 electrons in 3d. So why is this? 3d is our highest energy sublevel for chromium, and it's energetically more stable if 3d, that outermost sublevel, is half full, even if it means that a lower sublevel is unoccupied. This is one of the rare occasions where this actually happens, but the idea here is that a half-filled sublevel is sometimes more stable. For copper, we're going to see something very similar, and you might already imagine what that's going to be. Again, we're going to lose the 4s2 is going to become a 4s1, and that electron gets promoted so that our outermost 3d sublevel is completely full. Okay, the d sublevel has the maximum 10 electrons that it can have, and that's going to be more favorable, energetically speaking, more stable than having the 4s2 3d9. That wraps up our discussion on where electrons are arranged in the quantum mechanical model of the atom, or the wave mechanical model of the atom. Any questions you have about notation or orbitals, make sure you write them down and bring them in with you to class.